right, and we are live. What is up, everyone? I hope you all are doing well. My name is Ishan, and welcome to the video. In the last video, we spoke about the Europa Clipper mission that's going to Jupiter's icy satellite Europa to give us insights on its potential habitability for the sustenance of life under its icy surface. If you haven't watched that video yet, go check that out because it's a fun one. And in this video, I want to discuss Saturn's largest moon, Titan, and why it's such an interesting place in our solar system when searching for life outside of Earth. The emergence of life needs three key ingredients: liquid water, a specific chemical inventory of precursor molecules, and a consistent source of energy. Titan is one of the ocean worlds in our solar system that meets these three key requirements. With liquid lakes on its surface and a complex atmospheric and surface chemistry, Titan is a promising world to understand the origins of chemistry leading up to life and search for any signs of past or present life. Titan is the only moon in our solar system that is known to have a dense atmosphere which supports an Earth-like hydrological cycle, forming clouds, rain, and liquids flowing across the surface to fill lakes and even seas. However, these liquids are not liquid water, it is actually methane. Methane is the simplest hydrocarbon that is the main component of natural gas here on Earth. However, at Titan, the surface temperatures are so cold that it condenses methane, which is a gas, into a liquid, and that replaces the role of liquid water on Titan. The surface temperature of Titan is around 94 Kelvin or a negative 180 degrees Celsius, and that's hard to visualize, so consider this. It's so cold on Titan's surface that water solidifies into ice that is so dense that it actually acts as a rock. NASA's Cassini spacecraft was really the first time we found out more details about Titan's surface, because even though the two Voyager spacecrafts had observed Titan in 1979 and 1980, and we have some ground-based telescope observations as well, there's an organic haze in Titan's atmosphere that obscures the surface from visible wavelengths. So what the Cassini spacecraft did was use radar and imaging at near-infrared wavelengths, which was able to bypass that organic haze to give us a glimpse into what the surface really looks like. It mapped much of Titan's surface, measured winds, and imaged a small region of the surface in close-up detail. The observations from Cassini hinted to a salty ocean underneath the moon's water ice crust, earning it the title of an ocean world. Cassini showed us that Titan's surface has rivers, lakes, and even seas of liquid ethane and methane, as well as sand dunes. Like I mentioned before, methane forms the clouds and rains on Titan, much like water does here on Earth. With the atmosphere being 4 times as dense as Earth's and the gravity being about 1/7 as Earth's, raindrops on Titan fall significantly slower than that compared to Earth. And it is also quite rare. It may be centuries between showers at different locations. The dense atmosphere also protects the surface from intense radiation, which is important to preserve any biomolecules that might have formed. Titan's atmosphere consists of 95% nitrogen with about 5% methane, along with small amounts of carbon-rich compounds. Carbon-containing compounds are important because all of life as we know it is carbon-based. Titan's atmosphere has a lot of interesting chemistry going on because in the upper atmosphere, energetic particles from Saturn's magnetosphere and UV photons or solar photons, or sunlight in simpler terms, split apart the methane and nitrogen in its atmosphere to form low and intermediate mass carbon compounds, which can then recombine to synthesize more complex organics like benzene and acetylene, just to name a few. These complex organics then drift down to comprise the Titan's organic haze layer and are some of the building blocks towards more complex organic molecules that likely acted as the basis for the emergence of life here on the early Earth. So the more we study Titan and its chemistry, the more we can learn about how life arose on Earth and how it may arise in other worlds. This complex chemistry in Titan's atmosphere can precipitate down to the surface. The complex carbon compounds and organics can end up in a vicinity where liquid water was once available. So imagine sites like impact craters, which are places where meteorites strike the surface and in that process generate enough heat that it can melt water ice that's in that area, creating liquid water. And when these complex organics, carbon-containing compounds are present in liquid water, they can lead to certain chemical reactions and pathways that can form the building blocks of life, things like amino acids, nucleobases, lipids, things that life incorporated here on the early Earth. And these can be trapped in water ice as the liquid layer starts to refreeze over the course of time. Overall, Titan is one of the most fascinating places in our solar system to learn about prebiotic chemistry that may have led to life on the early Earth, while also looking for potential biosignatures, or in other words, signs of any past or present life or any building blocks of life that life uses. Lucky for us, there's a mission named Dragonfly that's going to Saturn's largest moon, Titan, in the next decade that is going to study its chemistry and search for biosignatures, but more on that in the next video. If you made it this far into the video, I just want to say I appreciate you so much and thank you for tuning in. If you got something out of the video, be sure to hit that thumbs up button, comment down any questions, thoughts that you have, or any topics that you might want me to make videos on related to space sciences and the search for life outside of Earth. And if you're new to the channel, don't forget to hit that subscribe button so you don't miss out on any future videos. I will catch you all in the next one.